Okay, so we're going to take a look at a few more examples here, finding limits algebraically. And I want to look at what happens when we have a vertical asymptote for a function. If I take the limit as x approaches 2 here, clearly you see the denominator is 0, so it's not continuous. We can't plug in directly. But notice when I plug in 2 up top, what do I get? 2 squared is 4 minus 1, I get 3. The form of this limit is 3 divided by 0. Okay, 3 divided by 0 is not an indeterminate form. And what do I mean by that? This tells me that I have a vertical asymptote. Okay, so anytime you have a non-zero number divided by 0, that's not indeterminate. This tells us we have a vertical asymptote. At x equal 2. Now, the minute we have this, we need to take a look at the limits from the left and right. Okay, and so what I need to immediately take a look at is what's the limit as x approaches 2 from the right, from the positive side of this function, and what's the limit as x approaches 2 from the negative side. Okay, now how do I do this analytically? What you should know is if we have a vertical asymptote, these are going to be infinite limits. The question is it plus infinity or minus infinity? Is it plus infinity or minus infinity? Well, the way I like to do this one way is to just think about this. When I plug in x equal 2, as x gets close to 2 from the positive side, what are we talking about? We're plugging in values bigger than 2, like 2.1, 2.01, and etc., right, from the positive side. Now up top, we're getting closer and closer to 3 still. And the bottom, we're getting closer and closer to 0. But the way I like to say it in this place is, I'm getting closer and closer to 0, but since we're always plugging in a number greater than 2, like 2.1, 2.01, and so on, this difference, x minus 2, is always positive. So I'm going to say I'm approaching 0 from the positive side. The top is always close to 3. That's a positive number. The bottom is always close to 0, but it's a positive number. If I take 3 and divide it by a smaller and smaller positive number, a number getting closer and closer to 0, then that is going to go to positive infinity, or just infinity is the way we write that. Contrast that here, if x is approaching 2 from the negative side, right, then up top we're still approaching 3, but down below what's happening? We're approaching what? Less than 2. I'm plugging in like 1.9. That difference is negative 0.1. 1.99. That difference is negative. So we're approaching 0, but from the negative side. And a positive divided by a negative is what? Negative. And so this is going to be negative infinity. Negative infinity. Okay. Alternatively, I mean, you could also do a table of values for this function and just confirm this. I've already entered into my calculator this function here. You know, we can look at it from a table standpoint. Here I'm approaching 2 from above, right? 2.3, 2.1, 2.01, so I'm getting closer and closer to 2 from above. Right, that's this limit here. And notice what's happening to our functional values. They are becoming unbounded. They are getting larger and larger. We're not approaching anything. We are going to positive infinity. If I approach 2 from below, like 1.8, 1.9, 1.99, and so on, then what are we doing? Notice we're always negative, as I said, and we're approaching negative infinity. Okay? Now, confirm that with the graph. Here's the graph of that function. We see the vertical asymptote at x equal 2. And indeed, as we approach it from the positive side, what's happening? We're going up to positive infinity. As we approach it 2 from the negative side, we're going down to negative infinity. So you're going to know you have a vertical asymptote if it's going to be the form any non-zero number divided by 0. If it's 0 over 0, then we're typically going to have a hole in the graph. Right? But if it's 3 divided by 0 or any non-zero number divided by 0, that's going to be a vertical asymptote. And you immediately, in that case, have to look at these two. Now, if I go back to the original question about what's this limit, I can now answer it, right? The limit as x approaches 2 of x squared minus 1 over x minus 2, that does not exist. Why? because from the left we're going to infinity, from the right we're going to negative infinity. Okay, the limit actually doesn't exist at all as a finite value from the left or from the right, but we do say the two-sided limit could be infinity or infinity, but that's only if what? If both sides are going to positive infinity or if both sides are going to negative infinity. Okay, but that's the way you want to analyze it the minute you get an indeterminate form that is of some non-zero number divided by 0. Okay. Another thing is we sometimes evaluate limits that have a parameter or a symbolic constant, and so we're going to evaluate this limit assuming a is a constant. So a is not a function of h. A is not changing as h changes. H is changing in this limit. H is going to 0, but a is some fixed value. We don't know what it is. But if I plug in h equals 0, what do I get? I get 3a squared minus 3a squared is 0. And of course in the denominator I get 0, and it's indeterminate. So we're going to do some work here. Don't forget my limit sign. What can I do? Well, I can expand a plus h. I hope everyone knows how to expand a plus h by now. And then I can distribute this 3 through. Three times 2 is 6. Okay, and then what I have, 3a squared minus 3a squared is 0. I'm left with 6ah plus 3h squared all over h. Okay. Now what? Well, notice up top I have that common factor of h as we expected to have. Let's factor that h out of the top. That leaves me 6a plus 3h. Right. Now these h's will cancel, and I'm left with the limit as h goes to 0 of 6a plus 3h. And now I can plug in directly. Notice that what I'm plugging in for is h, right? A is a fixed constant, so it's just going to be 6a plus 3 times 0, which is 0, and I just get 6a as my answer. So the limit, it's no coincidence that the limit is expressed in terms of this constant a. So the limit as h approaches 0 of our original expression equals 6a. We're done. There's the answer. Now we're going to be doing quite a few of these later on as well, so you need to get used to working with these symbolic constants. And there's some in the homework you'll be trying where, not only are we taking the limit as h goes to 0, but I can take the limit as, a approaches something. So you could change up which one is constant and which one is not. Okay. But the instructions should be clear what is constant and what is not. All right, a couple more examples to finish with. This one is an example involving two of our techniques. If you plug in directly h equals 0, and you should, you're going to get 1 divided by square root of 4 is 2, so 1/2 minus 1/2. Clearly that's going to be indeterminate form, right, that we've seen. Now, what I'm going to do first is I'm going to clear out the compound fractions. I have two smaller fractions within the bigger fraction, and the way I'm going to do that is with what I showed you last time, my method 2. I'm going to multiply the numerator and the denominator by the least common denominator of all my fractions, all my little fractions. Of course, this is h over 1 down here. So what do I have? I have a 1, square root of 4 plus h, and 2. So that means 2 times the square root of 4 plus h. That is my least common denominator. And I'm going to do that to the bottom as well. So I'm multiplying by a grand total of 1. And now what happens up top? When I multiply this whole thing, I have to distribute it over these two fractions. And when I multiply it by the first fraction, the square root of 4 plus h will cancel with the square root of 4 plus h, leaving me 2 times 1, which is just 2. Right? This times that gives me just 2. Now when I multiply it by a half, the 2's cancel out, and I'm just left with the square root of 4 plus h. In the bottom, I'm just going to multiply h times 2, or 2h times the square root of 4 plus h. Okay. So did that clear out my compound fractions? Yeah, I don't have smaller fractions within my bigger fractions. But now, if I plug in h equals 0, right, I get 2 minus square root of 4 is 2. 2 times 0 is 0, right? 2 minus 2 is 0. It's 0 over 0. It's still indeterminate form. Still indeterminate form. Okay. What can we do now? Well, now I'm going to use that technique of multiplying by the conjugate, and I'm going to do the conjugate up top, because notice this is 2 minus the square root of something. I'm not subtracting anything down here. This is 2 times h times the square root of 4 plus h. So I'm going to multiply by 2 plus the square root of 4 plus h. Okay. And now this gets quite involved here, but we'll just take it one step at a time. Up top, I'm going to FOIL it out. 2 times 2 is 4. The outer is 2 times the square root of 4 plus h. I'll just go ahead and rewrite that out here. The inner is negative 2 times the square root of 4 plus h. But you know what happens to those inner and outer terms when we multiply by the conjugate. These are going to combine together to give me what? 0. And then minus times a positive is negative. Square root of 4 plus h times square root of 4 plus h is 4 plus h. And you want to be careful to do what? Put that in parentheses, because then you'll distribute. It'll be negative 4 minus h. Down below, I've got what? I'm just going to multiply all this together. I'm not going to distribute down here. I want to leave this factored down here. So I'm going to put this in parentheses, what? Times 2 plus the square root of 4 plus h. Whew, okay. Now, this does simplify quite a bit, because this is 0. And what do I have? This becomes what? 4 minus h. So the 4 minus 4 is 0, and I'm just left with 0 minus h, or negative h. Okay. A lot of writing going on there, I know. We can proceed now, because why? We've got this common factor of h, right? H over h is 1. And what I'm left with now is, the function that I'm left with now is identical to our original function for all values of h except h equals 0, but this one is continuous at h equals 0. And I can show you that by plugging in directly h is 0. The top is negative 1. The bottom is 2 times the square root of 4 plus h, where h is 0, times, in quantity, in parentheses, 2 plus square root of 4 plus 0. Okay. Square root of 4 plus 0 is square root of 4 is 2. This is 2. So I've got 2 plus 2 is 4. 2 times 2 is 4. 4 times 4, I get negative 1/16. Negative 1/16 there. So there's an example of where you're using two techniques. So sometimes you might have a function where you're taking the limit of, and you have to use one technique for one part and one technique for the other part. And you can use the basic limit laws. In other words, the limit of a sum is the sum of the limits, or the limit of a product is the product of the limits. You can use those techniques as well. So the last example I want to look at involves a different indeterminate form. At the very beginning, if you remember, and I've got that page right here, we talked about indeterminate forms 0 over 0, which we've dealt with exclusively. But I want to look at 1 infinity minus infinity. Now you might say infinity minus infinity, isn't that 0? Isn't anything times itself 0? But again, infinity is not a number. What we're saying is basically, when we say a limit's infinity, it's like a vertical asymptote, right? And if you have a vertical asymptote, let's just say I have a vertical asymptote here, you can have two functions approaching that vertical asymptote in such a way. Let's say this is one, function there, and here's our other function. It's also going to infinity, And the difference, though, what we're doing is subtracting, so the difference between them could be getting close to the same value. It could be getting close to the same value, so the difference could be some finite number. Now, if they're getting closer and closer together, maybe on this side, we might have them getting closer and closer together as x gets closer to it from this side. So if the distances are getting smaller as we move, right, then we could be going towards 0. The limit could be going towards 0. So it just depends on how these two functions are behaving, right? Is the bottom function, are they getting closer to each other as they go to infinity? Are they getting further apart? We don't know. So it's indeterminate. And you can see this as I approach 3 from the positive side, I'll have 2 divided by 0 if I plug in, which tells me I have an infinite limit, as we saw a little while ago. But notice, since I'm approaching 3 from the positive side, x is always going to be something a little bit greater than 3. So this is approaching 0, but it's always positive. So this is going to positive infinity. It helps to factor this denominator. We can do that pretty easily. This factors as what? X times x to x, give me x squared. What do these two factors have to be? They have to multiply to 6, but add to -5. So what's the answer? -3 and -2. Right? So again, now if I plug in a value 3 that's value of x that's close to 3 but always bigger than 3, of course this is going to be close to 1. 3 minus 2 is 1. But this will be, what, a little bit bigger than 3 minus 3. This will always be a positive number, but it's going to 0. So this is approaching 0 from the positive side. 2 divided by something going to 0, that is also going to be infinity. All right? So this is going to be of the form, this is going to be 2 divided by 0 from the positive side, which is going to infinity. So the bottom line is all this analysis simply means we have infinity minus infinity. Okay? So how can we evaluate a limit like this? How do we know what it's approaching? I can't plug in directly, obviously. Is infinity minus infinity 0? Is it infinity? Is it something else? Okay, well, what can we do algebraically? Let's just look inside the parentheses. What do you think you could do to that expression to change it into something else? Anything you can think of? I hope you're thinking of subtracting by finding a common denominator. And what is the common denominator? Here we factored this one, x minus 3, x minus 2. Here I have x minus 3. So it's the common denominator that we want to use is this one right here, x minus 3 times x minus 2. So I need to multiply numerator and denominator of this fraction by x minus 2. So there it is. I multiplied top and bottom by x minus 2 of this fraction. So I multiplied by a grand total of 1. I haven't changed anything, right? Here I still have 2 over, we'll go ahead and write the factored form. Right? And now I have this common denominator, so I can subtract this minus this. Of course, let's go ahead and before we subtract, let's distribute this 2 through. And I get 2x more. And so, what do I have? The limit as x approaches 3 from the positive side. 2x minus 4 minus 2 all over x minus 3 times x minus 2. Okay. And what does this up top simplify down to? Can I combine some like terms? Yeah, negative 4 minus 2 is negative 6. I get 2x minus 6. And now, again, if I plug in x equal 3 right now, notice what you have. 2 times 3 is 6. Minus 6 is 0. And obviously I get 0 down here. I'm back to my 0 over 0 form. This is back to 0 over 0 form. But notice I can go ahead and factor that 2 out of the 2x minus 6 up top, leaving me x minus 3. And there's my common factor of x minus 3. And so it's just 2 divided by x minus 2, and I can plug in directly now, right? Replacing x with 3. 3 minus 2 is 1. 2 divided by 1 is just 2. So in this case, infinity minus infinity equals 2, which means these two functions, 2 divided by x minus 3 and 2 divided by x minus 3 times x minus 2, they're both going to infinity as x approaches 3 from the positive side. So we're coming from the positive side, so they're both going up to infinity, but the difference between them is getting closer and closer to 2. Okay. Again, you can check this numerically. Take this function in your calculator and plug in values closer and closer to 3, but only from the positive side, so like 3.1, 3.01, 3.001, and so on. What are you getting closer and closer to? You should see that you're getting closer and closer to 2. Okay? That confirms your result, but your support has to be done algebraically, as I've done here, showing each step using correct limit notation, right? You get rid of the limit only when what? You've plugged in x equal 3 here, and then you don't need the limit sign anymore. Okay, so there's lots more examples we can do, but you've seen a little bit of everything in these 3 videos. And so you want to continue to practice the homework problems. That's where you're going to learn it. You have to take ownership in this process. So this is tough. Some of these expressions are, you've got to do some algebra, some simplifications, and some work. So definitely going to spend a lot of time on these, and I encourage you to do so. And we will continue in our next lecture. We're going to be looking at limits involving trigonometric functions. Woohoo! Excited about that.